Hello and welcome to the official channel of Concept Clarity 101, empowering your journey with practical insights. Dear students, today in this video we will be covering the entire unit of carbon and its compounds. So stay tuned for this amazing session where we will clear all your doubts. Let us first discuss the background history of organic chemistry and its definition in the earlier times. Well, before the start of fancy labs and microscopes, early humans have been able to distinguish different kinds of material. Like they burned wood for warmth, not the rocks. They ate fruits, vegetables, and meat. Back then, why remained a mystery? Things were known at a bigger picture level, but not the tiny blocks that made them unique. So dear students, until 19th century, organic compounds were defined as compounds that could only be derived from living organisms. And Jacob Berzelius proposed a vital force theory. He said that life cannot be created in laboratories. Hence, organic compounds cannot be synthesized as they possess some mysterious forces which he named as vital forces. While inorganic compounds that were synthesized in laboratories lack such vital forces among their constituent particles. In 1828, Friedrich Wohler accidentally discovered urea, a well-known organic compound present in the urine of man and other mammals. Wohler took two inorganic solutions of ammonium chloride and potassium cyanide, heated and obtained ammonium cyanate and potassium chloride. Ammonium cyanate being unstable on further heating produced urea undergoing rearrangement reaction. Thus, chemists redefined organic compounds as compounds that contain carbon. Now, what makes carbon so special? The tiny blocks called carbon that makes up almost everything for living, from DNA to proteins, vitamins to enzymes. Carbon is always there. But wait, carbon is not just for life, it is also in clothes, plastic, and even medicine. Thus, there is a whole world of carbon out there. So, get ready to level up your knowledge on carbon. Dear students, carbon is positioned at number 6 in the periodic table. Therefore, carbon has got 6 electrons and 6 protons. The mass number of carbon is 12, which means it has 6 protons and 6 neutrons. We know the first electron shell, that is K shell, can hold 2 electrons, and second shell, that is L shell, can hold 8 electrons. Since carbon has 6 electrons, its electronic configuration can be written in two ways: K2, L4, where K is the first shell and L is the second shell, or its electronic configuration can be written as 1s2, 2s2, 2p2, where S and P represent subshells. Most important shell of an atom is its outermost shell, and carbon has 4 electrons in its outermost shell. So, to become stable, we may say carbon can lose or gain its 4 electrons. Thus, valency, which is the combining capacity of any element, and the valency of carbon is 4. But carbon cannot afford to lose or gain electrons because large amount of energy is needed to overcome forces of repulsion between the electrons, or large amount of energy is needed to remove 4 electrons from carbon atom. Dear students, we know ionic bond is formed by transfer of electrons from one atom to another atom. For example, NaCl, which is named as sodium chloride, consists of sodium and chlorine. The sodium has atomic number 11 while chlorine has atomic number 17. The electronic configuration of sodium is K2L8M1 while electronic configuration of chlorine is K2L8M7. Therefore, sodium loses its one electron and develops positive charge, thus becomes stable, and chlorine gains one electron and develops negative charge. But carbon cannot form ionic bond. So, how does it become stable? Well, it becomes stable by equally contributing its valence electrons with its combining atoms. Therefore, such bond, which is formed due to equal sharing of electrons, is called covalent bond. So we can say carbon always forms covalent bond. Now, let us discuss how covalent bond is formed by drawing Lewis dot structures, which is a simplified representation of valence electrons. Let us take an example of carbon dioxide. Carbon dioxide is made up of carbon atom and two oxygen atoms. We know the carbon has atomic number 6 and its electronic configuration is K2L4 while oxygen has atomic number 8 and its electronic configuration is K2L6. Dear students, before drawing Lewis structures, you must keep some rules for drawing the structures of various compounds. Rule number 1. Only show the outermost electrons or valence electrons when you draw the Lewis structure. It works on octet rule, which means atom must have 8 electrons in valence shell except hydrogen, which keeps 2 electrons. Rule number 2. Rule for selecting central atom. Always give priority to the atom which is present in least number, then to the least electronegative atom, or to the atom which has highest atomic number. Note: hydrogen and fluorine can never be central atoms. Rule number 3. Octet of corner atom must be complete. For hydrogen, it must have its duplet complete. Rule number 4. Central atom can have 8 or more electrons. Now moving to the example directly. In carbon dioxide, there is one carbon atom and 2 oxygen atoms. Therefore, carbon is the central atom and two oxygen atoms are the corner atoms. Each oxygen has 6 electrons in valence shell and needs 2 more electrons to complete its octet, while carbon has 4 electrons in valence shell and needs 4 more electrons to complete its octet. Let us denote the electrons of carbon as red dots and electrons of oxygen as yellow dots. Carbon shares its electrons with the oxygen atom, and oxygen indeed shares 2 electrons with the carbon atom. Now one oxygen has its octet complete, and the carbon atom has now 6 electrons. The other oxygen atom also shares 2 electrons with the carbon. and carbon indeed shares its two electrons with the same oxygen atom. So, we see all the atoms in carbon dioxide have their octet complete, and carbon forms double covalent bond with each oxygen atom. Note, the electrons which are not involved in bonding are called as lone pairs, and the electrons which are involved in bonding are called as bond pairs or shared pairs. Example number 2, methane, which is written as CH4. In methane, there is one carbon atom and is present in least number, and there are 4 hydrogen atoms. Carbon, we know, has 4 electrons in valence shell and needs 4 more electrons. Hydrogen has electronic configuration K1, therefore has 1 electron in its valence shell and needs 1 more electron to complete its duplet. Now let us denote the valence electrons of carbon by yellow dots and electron of hydrogen by red dots. Hydrogen and carbon share 1 electron each and form 4 single covalent bonds. In this way, the carbon completes its octet and hydrogen completes its duplet. Dear students, here are some compounds for you to practice: C2H6, CCl4, H2O, Cl2, S8 and C2H2.
So dear students, there are millions of organic compounds known today. But what is the reason that carbon forms so many compounds? Well, the main reason for this is catenation and tetravalency. Catenation. It is the self-linking property of an element, due to which a large number of its atoms can be linked with each other. Carbon can combine with other carbon atoms to form straight or branched chains of varying lengths and rings of various sizes. Number 2. Tetravalency. In order to become stable, carbon shares its 4 valence electrons and forms 4 strong covalent bonds with other elements such as hydrogen, oxygen, nitrogen, sulfur, chlorine. This further increases the possibility of the number of carbon compounds. Dear students, you are likely familiar with pencils and their nibs, which help us write, as well as diamonds, which are used as jewelry. But did you know that both of these are made of carbon? Yes, you heard it right. But why do they look different and have different properties? The answer lies in the arrangement of atoms. When an element exists in 2 or more forms due to different arrangement of atoms having the same physical state is called allotropy. Carbon, for instance, has 3 allotropes: graphite, diamond, and fullerene. Let us discuss the 3 allotropes of carbon one by one. Diamond. In diamond, each carbon atom is covalently bonded to 4 other carbon atoms. The 4 surrounded carbon atoms occupy corners of a regular tetrahedron, thus forming a regular tetrahedral structure. The angle between 2 adjacent carbon atoms is 109 degrees and 28 minutes. The tetrahedron arrangement gives diamond a 3-dimensional structure which makes it rigid. Since there is no free electron in diamond, so it is a bad conductor of electricity. Because of hardness and very high thermal conductivity, it is used in cutting glasses and for drilling purposes. Graphite. In graphite, each carbon atom is linked to 3 carbon atoms in the same plane, forming hexagonal rings, leaving one free electron. The various sheets of hexagonal rings in graphite are connected by weak van der Waals force of attraction. Since it has one free electron, it is a good conductor of electricity. Due to its layered structure, it is soft and slippery. Therefore, it is used as lubricant. Now, fullerenes. First one to be identified was C60. It contains 60 carbon atoms arranged in the shape of football. It consists of 2 types of rings, 12 pentagonal rings and 20 hexagonal rings. Hexagonal rings are fused with other hexagonal rings and pentagonal rings, while pentagonal rings are fused only to 6-membered rings. Dear students, let us move towards another topic, hydrocarbons. Organic compounds of hydrogen and carbon are called as hydrocarbons. The hydrocarbons can be acyclic, which are also named as open chain structures. For example, propane. Or hydrocarbons can be cyclic, which are also named as closed chain structures. For example, cyclopropane. Cyclic and open chain structures can be saturated hydrocarbons or unsaturated hydrocarbons. Now, saturated hydrocarbons. Hydrocarbons in which carbon atoms are linked by single covalent bond are called as saturated hydrocarbons. For example, propane and cyclopropane. In these cases, all carbon atoms are linked by a single covalent bond. So we can say these compounds are saturated hydrocarbons. Saturated hydrocarbons containing open chain structures are called as alkanes. For example, propane. Alkanes are represented by a general formula CnH2n plus 2, where n is equal to 1, 2, 3 and so on. Value of n depends on number of carbon atoms. For propane, n is equal to 3 because there are 3 carbon atoms. Therefore, its general formula can be written as C3H2 multiplied by 3 plus 2, which is equal to C3H8. So, the general formula of propane is C3H8. Now, my dear students, you may also encounter hydrocarbons that contain at least one or more double or triple bonds. Such hydrocarbons are called as unsaturated hydrocarbons. For example, propene, propyne, and cyclopropene. Now, unsaturated hydrocarbons containing open chain structures with at least one double bond are called as alkenes. For example, propene. These are represented by general formula CnH2n. where n is equal to 1, 2, 3 and so on. And the value of n depends on the number of carbon atoms. In case of propene, n is equal to 3. Therefore, general formula of propene is equal to C3H2 multiplied by 3, which is equal to C3H6. Now, my dear students, unsaturated hydrocarbons containing open chain structures with at least one triple bond are called as alkynes. For example, propine. These are represented by general formula CnH2n-2, where n is equal to 1, 2, 3, and the value of n depends on number of carbon atoms. My dear students, imagine a world of chemistry where every scientist called molecules whatever they wanted. Back in the early days, chemists named a new molecule after the source it came from or based on some random observation. This made communication a nightmare. As the number of discovered compounds grew, it became clear that a consistent and universal naming system was needed. The International Union of Pure and Applied Chemistry IUPAC developed a set of rules for naming organic compounds so that every compound would have a unique and clear name. This system helps scientists around the world to communicate more effectively and avoid misunderstanding. So, my dear students, get ready to understand countless organic molecules by a universal language. Naming organic compounds, the golden rule. Dear students, when naming organic compounds, we follow the systematic approach using the components, secondary prefix, primary prefix, word root, primary suffix, and secondary suffix in the same order. Let us understand them one by one. Secondary prefix. It indicates substituents or side chains attached to the main carbon chain. But wait, what is this substituent? Well, a substituent is an atom or group of atoms that takes the place of hydrogen atom on a carbon chain in a molecule. So let me clear this with an example. Let us say we have alkane containing 5 carbons and 10 hydrogen atoms. If we remove one hydrogen, let us say this one, and we place chlorine Cl at its position. Now this chlorine is substituent. Thus, the substituents you will often see may be halogenous, alkyl groups, or a nitro group. Halogenous include fluorine, chlorine, bromine, iodine. For fluorine, secondary prefix fluoro is used, and for chlorine, chloro is used. For bromine, bromo is used. For iodine, iodo is used. Now this substituent can be alkyl group, and these alkyl groups include CH3. For its use, it is written as methyl at secondary prefix. CH2, CH3. It is written as ethyl. CH2, CH2, CH3. It is written as propyl. CH, CH3, CH3. it is written as isopropyl. Now primary prefix. It indicates the presence of cyclic structures. If the compound is cyclic, cyclo is used as primary prefix. Word root. It indicates the number of carbon atoms in the longest continuous chain. For one carbon atom, word root meth is used. For two carbon atoms, word root eth is used. For three carbon atoms, prop is used. For four carbon atoms, but is used. For five carbon atoms, pent is used. And so on. Now, primary suffix. It indicates the type of carbon-carbon bond. If the compound contains single bond throughout, an is used as primary suffix. Similarly, "-ene" is used as secondary suffix, which indicates double bond. "-yne" is used as a primary suffix, which indicates triple bond if present. Secondary suffix. It indicates the main functional group present in the compound. This functional group can be alcohol, aldehyde, ketone, carboxylic acid. The general formula of alcoholic group is ROH or simply OH, where R indicates long chain of carbon and secondary suffix used for alcohol is ol, OL. Aldehyde. For aldehyde, general formula is R C double bond OH or simply CHO. And secondary suffix used for aldehyde is AL. For ketone, general formula is R C double bond OR. And secondary suffix used for ketone is one, ONE. For carboxylic acid, general formula is RC double bond OOH or COOH. And secondary suffix used for carboxylic acid is oic acid.
Dear students, let us do the IUPAC naming of organic compounds under its rules. The first thing we always need to do while naming is identifying the longest carbon chain. In this example, the longest carbon chain has 4 carbon atoms and all bonds are single bonds between the carbon atoms. Therefore, we use word root meth and primary suffix "-an". Since there is no other prefix or suffix present, we can name this compound as butane. Example number 2. Compound with a double bond. Select the longest carbon chain, and here the longest carbon chain has 5 carbon atoms. Therefore, word root is pent. Primary prefix indicates that there is one double bond between carbon atoms, and you must keep a note here. Number the carbon chain so that double bond gets the lowest possible number. Always use hyphens to separate numbers from words. Thus, if we number from the left side, the double bond gets lowest number. Therefore, IUPAC name of this compound is pent-2-ene. Now, example number 3. Compound with an alkyl group. Before naming this compound, I want you to note, if a substituent or side chain is present, the numbering is done in such a way so that the substituent gets the lowest possible number. In this case, the longest chain has 5 carbon atoms and numbering will be done from left side so that CH3, a methyl group substituent, will get lowest number. 5 carbon atoms mean word root is pent. CH3 means secondary prefix is methyl, and there are only single bonds throughout, which means primary suffix is an. Therefore, IUPAC name of this compound is 2-methyl pentane. You must keep this thing. While naming, do not use spaces between parts of the name. Now, example number 4. Compound with an alkyl group and halogen. In this case, the longest chain has 5 carbon atoms, and numbering starts from and nearest the substituents. To give substituents the lowest possible number, so chloro gets position 3, methyl gets position 2, and there are only single bonds throughout. Now, IUPAC name of this compound is 3-chloro-2-methyl pentane. In this case, you might have noticed chloro is preferred over methyl substituent, although its position is 3 and methyl is at position 2. I want you again to keep a note here. The substituents are always named in alphabetical order. Therefore, we know C of chloro comes before M of methyl in the alphabetical series. That is why it is named as 3-chloro-2-methyl pentane. Example number 5. Compound with 2 different halogens. Dear students, in this example, longest chain has 5 carbon atoms. Therefore, word root is equal to pent. B of bromo comes before C of chloro in the alphabetical series. So, bromo is given priority over chloro, which means numbering will be done from left side. Thus, IUPAC name of the compound is 2-bromo-4-chloro-pentane. Example number 6. Compound with a double bond and alkyl group. Dear students, in this case, the numbering will start from the end nearest to the double bond, because primary suffix or double bonds are given highest priority over substituent. So, double bond will get position 2 and methyl will get position 3. Therefore, the name of the compound is 3-methyl pent-2-ene. Example number 7. Compound with identical substituents. Dear students, before naming this compound, I want you to know that always use di, tri, tetra along with the prefixes of multiple identical substituents. Di means there are 2 identical substituents. Tri means there are 3 identical substituents. Tetra means there are 4 identical substituents. And do not forget to use comma to separate numbers. In this case, 2 identical methyl groups get position 2 and 3. Therefore, we will add di along with the prefix methyl. So, IUPAC name of this compound is 2,3-dimethyl pentane. Example number 8. Compound with a ketonic group. Dear students, before naming this compound, remember this: main functional group is always given a highest priority and is indicated by a secondary suffix. In this case, the longest chain has 5 carbon atoms and a ketonic group C double bond O will get position 2. So, the name of this compound is pentane-2-ene. Please note it down. Always avoid double vowels. When primary suffix, for example in this case, an ends with vowel E. Write it as pentane-2-one instead of pentane-2-one to avoid combination of two vowels such as E and O occurring together. Example number 9. Compound with a carboxylic group. In this case, the longest chain has 4 carbon atoms and carboxylic acid group is on the first carbon. Please note this. Functional groups such as aldehydic and carboxyl group are always present at the end of the chain. Therefore, they are called as terminal functional groups. The IUPAC name of this compound is butanoic acid. Example number 10. Compound with an alcoholic group. In this case, the longest chain has 4 carbon atoms with alcoholic group or hydroxyl group on the second carbon. Therefore, the name of this compound is butane-2-ol. Now, example number 11. Ketone with a halogen substituent. In this case, longest chain has 5 carbon atoms with ketone on the second carbon and chloro group on the third carbon. Therefore, IUPAC name of this compound is 3-chloropentane-2-one. Example number 12. Hydrocarbon with double and triple bonds. Before naming this compound, I want you to note a molecule contains both double and triple bonds is called an alkyne. If both double and triple bonds are present at same positions, the double bond is always prioritized for the lowest possible number. In this case, longest chain has 5 carbon atoms. Thus, the IUPAC name of this compound is pent-1-in-4-ine. So my dear students, I hope that with these examples of nomenclature based on IUPAC rules, you understand the concepts better and will practice more advanced problems. I would love to hear from you in the comments section if I need to add more information or if you understood everything well.
Now let us move towards the another topic, homologous series. Dear students, we know alkanes are represented by general formula CnH2n plus 2. If n is equal to 1, it becomes equal to CH4, and the name of this compound is methane. We know adjacent to methane we have ethane with molecular formula C2H6, because in ethane n is equal to 2. Adjacent to ethane we have propane having molecular formula C3H8. Dear students, in all these alkanes we see only a difference in molecular formula. Now let us see how much they differ from one another. We know methane has molecular formula CH4, ethane has molecular formula C2H6, and propane has molecular formula C3H8. The noticeable difference between methane and ethane is CH2, and that of ethane and propane is also CH2. So we can define homologous series, a group of organic compounds having similar structures and similar chemical properties, in which the successive or adjacent compounds differ by CH2 group. Now, what are the characteristics of homologous series? Dear students, all the members of homologous series can be represented by general formula. For example, homologous series of alkanes can be represented by general formula CnH2n plus 2. Any two adjacent homologues differ by CH2 group. The molecular masses of any two adjacent members of homologous series differ by 14 atomic mass units, because in CH2, atomic mass of carbon is equal to 12 AMU and that of hydrogen is equal to 1 AMU, which means molecular mass of CH2 is equal to 14 AMU. Dear students, the pentane we know has molecular formula C5H12. Let us do the numbering on its carbon atoms. 1, 2, 3, 4, 5. Now displace one carbon atom and put it as substituent at position 2 and satisfy its valency by placing 3 hydrogen atoms on it. The IUPAC name of this compound is 2-methyl-butane, having molecular formula C5H12. Now, let us displace carbon at position 4 and put it as substituent at carbon 2 and satisfy its valency. The IUPAC name of this compound is 2,2-dimethyl-propane and the molecular formula of this compound is C5H12. The compound 2,2-dimethyl-propane is also named by its common name, that is neopentane. 2-methyl-butane is named by isopentane and pentane by N-pentane. The prefixes N means normal or no branch, neo means 2 branches, iso means single branch. Thus, if a given molecular formula represents 2 or more structures having different properties, the phenomena is known as isomerism, and different structures are called structural isomers. Thus, pentane that we discussed has molecular formula C5H12 and has 3 structural isomers: N-pentane, isopentane, and neopentane. Chemical properties of carbon compounds. Combustion reaction. Dear students, carbon compounds show combustion reaction, a chemical reaction in which a substance reacts with oxygen to give off heat. Carbon compounds such as methane, butane, ethanol react with oxygen, producing carbon dioxide, water, and a lot of heat along with a flame. Oxidation reaction. Dear students, during combustion, the compound gets oxidized completely, or we can say there is complete oxidation. Oxidation in simpler terms means addition of oxygen. Now, my dear students, there are reactions in which partial oxidation takes place. This partial oxidation of substance is carried by oxidizing agents, which provide oxygen to the reacting substance. For example, alkaline potassium permanganate is a good oxidizing agent. Ethanol reacts to the oxygen provided by the oxidizing agent potassium permanganate and forms ethanoic acid and water. Number 3. Addition reaction. The reaction that involves addition of two reactants to form a single product is called addition reaction. Unsaturated hydrocarbons react with hydrogen in presence of a catalyst, which generally enhance the rate of reaction. This catalyst can be nickel, platinum, palladium. Saturated hydrocarbons, for example, ethene reacts with hydrogen in presence of nickel and forms ethane. This reaction is used in the hydrogenation of vegetable oils, which generally have long unsaturated carbon chains. Now, substitution reaction. Reaction which involves replacement of an atom or group of atoms by another atom or group of atoms. Organic compounds show substitution reaction. For example, chlorine replaces hydrogen on methane molecule and forms chloromethane and hydrochloric acid in presence of sunlight. Now, important carbon compounds, ethanol and ethanoic acid. Let us first discuss ethanol. Dear students, ethanol is the second member of the homologous series of alcohols, the first one being methanol. The general formula of ethanol is C2H5OH, or it can be written as CH3CH2OH. This ethanol is active ingredient in alcohols. It is also used in medicines such as cough syrups and many tonics. Now, chemical properties of ethanol. Dear students, ethanol reacts with sodium and forms sodium ethoxide with the evolution of hydrogen gas. In presence of hot concentrated sulfuric acid and unsaturated hydrocarbon, ethene is produced. Dear students, thus we can say hot concentrated sulfuric acid acts as dehydrating agent as it removes water from ethanol. Ethanoic acid. Dear students, ethanoic acid is commonly called as acetic acid. It is the second member of the homologous series of carboxylic acids, the first one being methanoic acid. The general formula of ethanoic acid or acetic acid is CH3COOH. A 5 to 8% solution of acetic acid in water is called vinegar. Now let us learn about the chemical properties of ethanoic acid. My dear students, ethanoic acid reacts with ethanol and forms ester, that is ethyl ethanoate, in presence of hot concentrated sulfuric acid. The esters formed here are sweet smelling substances and therefore are used in perfumes as flavoring agents. Number 2. Neutralization reaction. Ethanoic acid reacts with a base like sodium hydroxide to give salt, that is sodium ethanoate, and water. My dear students, carbon compounds are not just essential for life, they are everywhere around us, helping us in many ways. Soaps and detergents which we use for cleaning are also made from carbon compounds. Now let us discuss the chemistry behind them. Dear students, we know water and oil do not mix. But if you add detergent to water, they mix. So how does this happen? Well, we will know it. Mixing of water and oil in presence of soaps or detergents gives us a clue about how they help us in cleaning. Let us understand their basic structure now. Dear students, we know formula of sodium ethanoate, that is CH3COONA. Now if we replace this CH3 with a long carbon chain of hydrocarbon, now it becomes a long chain of hydrocarbon with a carboxyl group, that is C double bond OO. The molecule containing carboxyl part with sodium atom makes it a sodium salt of carboxylic acid. Now my dear students, we can define soaps. Soaps are sodium or potassium salts of long chain carboxylic acids, and the examples include potassium or sodium palmitate containing fatty acid palmitic acid, potassium or sodium stearate with fatty acid stearic acid. Soaps are made by a process called saponification, in which fatty acids, which are esters of long chain hydrocarbons, heated in presence of aqueous sodium hydroxide, which forms soap of sodium salt and a byproduct glycerol. Detergents, however, differ from soaps, as they are sodium salts of long chain sulfonic acids or sulfonates or ammonium salts. Now let us see how soaps and detergents work. Dear students, both soaps and detergents
consist of two parts. A negatively charged head. It is
hydrophilic part, meaning water loving, thus dissolves in water. A long hydrocarbon tail, which is non-polar hydrophobic part, meaning water hating, that loves oil or grease. When we mix soap with water containing oil or grease on clothes, hydrophobic part attaches to the oil or grease and hydrophilic head sticks out in water. Soap molecules surround the dirt and form a ball-like structure called a missile. The grease is trapped inside the missile. When we rinse, the water-friendly head helps us wash away the entire missile, taking the grease and dirt with it. This is how soaps and detergents help in cleaning.
Dear students, I hope you have thoroughly learned about carbon and its compounds and enjoyed the content. Please remember to like, share and subscribe to the channel. Do not forget to leave your feedback as we always grow together.